Hello. Morning.
Morning.
Morning. Hi. All right. So welcome to the meeting. So yeah, we had good week. We had one meeting. We had DevoWorm, and we talked about two papers in that meeting. We talked about a C. elegans paper on egg-laying strategies, like biological variation in egg-laying. And we talked about sort of the difference between E. coli information processing and C. elegans information processing, what you might call a motor circuit. And so that was kind of an interesting article as well. That's on the YouTube channel, on the DevoWorm channel, and it should be the latest video there. Other than that, we didn't do any cybernetics or cognition future meeting. We do have some news on the open source front, although we didn't have a meeting this week. So a bit of good news for the lab, I guess. I submitted two things to the active inference workshop, the one upcoming next month, and that was accepted, or both of them were accepted as as content for their workshop. So we're doing this open source session, and we're doing, it's kind of open source, open science. I just kind of put in a short description, but it's really going to be up to us to find the programming and fill it in. And then this other talk on the stuff that we were talking about with the Rosenbluth paper. So I think that's actually, kind of, it'll be interesting. I don't know. It'll be kind of like a lot of the work we've been doing in cybernetics. And we'll have to work on that. So, any questions or comments?
Just, let me know what you think would be appropriate in terms of in terms of the kind of the open source
Content, yeah.
Content, or would it be more like, how open source potentially powers open science, or
Yeah, the latter might be interesting, because what they're doing in Active Inference Lab is they're doing a lot of like participatory scholarship. So they're doing things with, building software for some things. They have people who want to access different tools. Like, it's like kind of a clearinghouse for open or for active inference in some sense. And so they have like a lot of, they want to do things like they have a lot of meetings, they have a lot of live casts that they want to create artifacts for, so like articles. And so there's a lot of open science. There's a fair amount of open source, and I don't know like how I think open source empowering open science would be a good topic, or at least like kind of a focus.
Yeah. Well, I'm always interested when I see the kind of the projects that they do, or the kind of the speakers they get are interesting. Do you know if they've already got some of those people? I mean, in terms of like RX and Fur is kind of a Julia drone project.
Oh,
for instance.
I don't I don't know who's speaking, or I think I
Oh,
saw
okay.
a draft. I don't know if I really paid a lot of attention to all the speakers, but they do have like. Oh, go ahead.
Yeah, I mean, would you be interested in speakers, or is it more putting together a presentation?
Well, I think we could have like someone like we could have our own sort of informed by our own experiences or our own
Mm,
working group,
mm,
and then we could have like one or two speakers. I'm not really sure how long this is going to be. I'll have to work out those details, but it might be good to have one if
yeah,
someone
well,
has a good perspective on things. We could
the
invite them.
the guy I was thinking of, I mean, like I said, like Nerd Desktop guy, Nerd Desk is guy is usually up for a presentation, but with that kind of topic, it might be interesting. The head of or the kind of like lead developer for SPM, right? So this is the MATLAB package that Carl Friston originally developed, and has become this kind of much greater kind of project. He's really interesting because he's a core developer to Octave. So like as a part of his work at SPM, which has always been a GPL project, um, like MATLAB's kind of hit this point where a lot of people like either can't afford MATLAB or kind of don't want to use it on clusters or things like that, right?
Yeah.
Anyway, so he started contributing to the Octave project. Um, at least, I mean, I talked to him years ago about it, and he was quite a significant contributor. And they were Octave was actually getting money from, I think, the EFF, and the EFF would see, it like, kind of a strange project for Octave, to support Octave, or funny to have the EFF support Octave.
Yeah.
But their point was that this would, like, making Octave better would free so much other uh, stuff. Like, people had written so much stuff in MATLAB
Oh yeah.
that contributing to Octave would kind of free and make sustainable all this MATLAB code that had been developed for so long. And like that could be, is like, again, like him speaking about that in terms of just as kind of, as it relates to software sustainability, and so
Right.
and kind of like the GSOC project itself, right?
Right.
That would be Guillaume. I'll check. It would be good to get in touch with him. It was
Yeah.
really nice.
Yeah.
Yeah, he was. Yeah, happy to talk about it.
Yeah, that would be a good topic. So, like, they do open source software there. They have a couple of research initiatives, and having like some sort of, like something on that isn't just kind of like, here's what is open source, but like a topic in open
Yeah,
source would be good.
yeah.
Yeah.
I mean, that would be kind of cool. It's kind of like talking to, was it Brian Ripley about R? Like if R had never been developed, like a lot of S and a lot of mathematicians' work would have been kind of lost to this closed source, kind of atrophy of that company.
Mm.
For sure. And then it's like mid-November. When is that? Yeah, I was gonna ask
The
one.
13th through the 16th or yeah, 13th through
Okay.
the 16th of November.
Yeah.
Yeah.
Yep.
So, yeah, I guess we can kind of come up with a little bit more formal. Well, I guess at this point, it's kind of open. I think it's going to be mostly virtual, so I think it might be like asynchronous in some sense. So we might just have like a session.
Yeah. Plus, Kiyoma like it because it's also Friston related.
Oh,
Friston adjacent. Well, not even adjacent. It's definitely Friston related. Yeah.
Right. Yeah. Well, Friston's on the scientific advisory board, or at least he was last year.
Yeah, for sure.
Obviously,
yeah. But it would be, so it would be nice to talk about their. Well, it's very much Guillaume's effort. This isn't something that he was made to do. This is just something where he saw great interest. He basically uses SPM as a great use case for octaves, for figuring out what like octaves limits are, and especially as it relates to GUI widgets and some other. Yeah. So because it's such an old project that goes back to like the early 90s, because like all these things about it just make it a great example.
Yeah, that's great. Yeah. Well, we'll see what we can do. Yeah. And we'll kind of do some programming. I don't know if Jesse, you got excited about this too. So I don't know if you had something to say about
it. Not, I mean, a lot of things have been covered already, but more just curious about what, like, do we have I feel like I'm either forgetting or just haven't seen some of the details. Like, how much time for like, is it like an allotted amount of time we get, or like, how does that work for like that part of it? I know there's a few things going on. Like, there's like the submission that's like the paper or whatever, but then there's also this potentially panel, potentially whatever. Like, I guess I was curious about the details for that we could make programming for.
Yeah, so it seems pretty open ended at this point. We have for the cybernetics talk, it's anywhere from 15 to 45 minutes, and I think it's up to our discretion as to how much time we use. So it could be like, it's something we pre-record, and it's like, basically I think it'd be closer to 45. And then the open source stuff, I'm not really sure what Daniel's thinking for that, but it definitely would have like maybe an introduction. We'd want to highlight what we've been doing in our open source interest group, how we kind of think about open source, or I don't want to get into like what is open source. I think a lot of the people attending this are savvy enough to know that. To have like I think what Morgan was talking about is kind of good, having like an open source for open science, and then having like a guest speaker on a topic that's maybe really relevant to active inference. And I don't know how much time we have for that, but well, I think he wants to have this as sort of like workshop that's like I guess what he wanted, and we talked about this kind of informally, sort of an open source presence so that people could get exposed to it. I'll have to work out the details later, but if you have something that you're really interested in, and I know you've been interested in open science and some of that, we should talk about it more.
Yeah, like there's a little bit of a dovetail into I guess its official title was the ICOR public meeting, which focused on advancing open research through meta science this week. ICOR is the advancing, what is it? Through open research. It's not showing up for me.
Yeah, it's about to collaborate and open research.
Well,
incentivizing collaborative artwork, right?
Yeah, incentivizing is the I word. And that was a fun, interesting thing to see. So, I mean, it's not like I can just take things from that necessarily, but that was exciting in terms of looking at meta science. So maybe I'll look more into like meta science applications, but also like, I mean, I don't quite know there's things from like almost a pedagogical or a mentoring, or like how do you run a lab that does this thing, or how do you create open source, we have a lot of things in the open source sustainability space that are applicable. So I guess it's just we can talk more about what are the targets that we want to hit, I suppose. But yeah, that sounds promising.
All right. Yeah, this is, I mean, it's both in the future and almost not. You have like about a good month left, or maybe 6 weeks to do this. So.
Yeah.
All right. So that's good. Well, we'll stay on top of that. Hopefully, I can get more details and we can work on it more.
Yeah. It'll be. Yeah.
So hello, Sarrah and Hussain. I don't know if you have any updates to share with us.
Hi.
Hey.
Hi.
Yeah, you go ahead.
Okay. Who wants to go first?
Sure, I can go first.
Okay.
Yeah. Okay, so I've been working on the breast cancer convenience demography project alongside Dick. We've been making some good progress. We just submitted our manuscript to the Journal of we just submitted the manuscript for publication, so that's good. It's the best thing we're doing. Okay. Yeah, we've been moving into collaboration, moving into new steps with other professionals who are getting on board as well, looking for ways to secure funding, like through different programs with the NVIDIA grant program and via academic grant program. And I've been finding some new tools and software for different sorts of approaches. And yeah, that's basically it, because there's a lot to talk about. But we've been making some really, really good progress. Ultimately, it seems like the technology, once again, has a lot of potential. I've already reached out to patent firms, by the way.
Okay.
Reached out to patent attorneys. I don't mean to jump the gun, putting the cart before the horse, because we're not published yet. But like legally, you kind of need to get on it pretty soon. You need to get on it pretty quickly. Like in America and Canada, there is if something has been publicly disclosed, so like you post about something, you publish something, you cannot patent it. But there is a 1-year grace period from when something has been disclosed for the person who disclosed it to file a patent. Normally in other countries, I don't think they give you so much of a grace period, because the patent technology has to be something like new, something novel. So if it's disclosed and people are talking about it, then you cannot patent that. So basically that's where we are right now. Yeah, still looking through a lot of papers, trying to do a lot of work. And it's still just frustrating that I'm doing all this without, it's all voluntary still.
Right.
But we are applying to grants, we're reaching out. I posted a few. In the chat.
That's good. Thank you for that update. It sounds like you're having a good collaboration. Sarrah, are you there?
Yeah.
Okay.
Hi. In terms of updates, there isn't like much really. Like the week before last, I put up on the channels that I was doing the GSOC Lightning talk, and like a week before I did the talk as well, like there were so I had to prepare like some slides for it. So I also thought it would be a good time to like make a good demo video of like the entire project. So I did that and then Bradley published it to our YouTube channel. So there's like a proper like video of the entire simulation running. So like even during my final presentation, there were like a few kinks. So those are all cleared out. But yeah, since the GSOC, since the talk that I did, like I haven't really been able to do anything much on the project. So like I started a new job. So I've been like, a lot of time has definitely been going there. But it's exciting there as well. And even like doing the talk, like when I looked at the code again after like a break of like 2 weeks. So this is like, I was able to get it all done. And then like something that I definitely want to, ask in the coming weeks is like, how do I, like now that we have the whole simulation running, what kind of like runs do we do to, like when we were talking about a publication, I remember Bradley being like, we'll have to have some kind of like statistics of different kinds of runs that we do and have some kind of data. So definitely want to like talk more about what kind of things I can do there, and because it will take some time because the simulations on the thing take quite a long time to run. So that is something that I definitely want some like advice on like how to proceed in that direction. But I haven't like yet asked for it because the new job is kind of busy in the starting weeks. So once I like settle in there, I'll definitely like come back for advice on that. So yeah, that's about it from my side.
Okay, that sounds good. Yeah, thank you. So congratulations on your lightning talk. I didn't get to see it, but I mean, hopefully it went pretty well. It was well received.
Yeah, sure. I even have like a video of it that someone recorded, like a screen recording. So I'll post that in the research channel if anybody wants to have a look. It was quite good. It was just 3 minutes. So there wasn't like any kind of like in-depth or any Q&A or anything, but like I got to present it nicely.
Yeah, it's good. Well, yeah, and please post that when you can, when it's up. And of course,
I don't know if they are going to be posting it officially anywhere. I do have like a video that was just like screen recorded.
Okay.
But yeah, I don't know if there's like a YouTube link or I don't think there is.
Oh.
But like, yeah, I just have one for personal purposes. If I can put it up on the GSOC Slack channel, would that be like okay, or am I not supposed to?
Yeah, you can do that. Yeah.
Yeah,
please
sure.
do.
I'll put that up then.
All right.
That'd be great.
Yeah, thanks.
Yeah, and then of course we have your little demo that we had on the YouTube channel. So it's like a minute-long demo, kind of walking through the software, and yeah, so that's on the YouTube channel. And then the manuscript. Yeah, we should start thinking about that. It's I don't know exactly how we want to do this. I imagine we could probably just like, have a, any manuscript you'd have to have some sort of, literature review and introduction, and then, the way you test it out maybe would be to set up a few sample tasks like you were doing for your GSOC project, but maybe make a few more tasks that, generate them through autocode rover and or whatever. I can't remember the actual steps, and then run through a couple of scenarios. So you kind of set up a couple of kind of like, this is a task, and we might have like 3 or 4 conditions like that, and then you run through it and you show how those tasks are solved. And then I don't know if we can, well, we probably start there, and then maybe like do some more experiments later depending on what the results of those are. We could do benchmarks where you test each task, so you might have different types of tasks, like different in open source we have different types of issues, or different types of projects where they involve different types of skill sets, different types of agents, and we can kind of come up with some basically experimental conditions compare them, benchmark them, and everything. And I think that might be a good paper. And that's that's something we can, I think, get a lot of useful information out of. And we can actually, and of course, there's the other paper where we have sort of the write-up of all the different projects that we have that needs to be updated. So there's a preprint on ResearchGate right now, which has all of the different models that we've done for open source sustainability. We have an active inference model. We have some work done on the reinforcement learning. We have a personality model. And then now we have the large language model approach. So we put all those kind of in the list. We say, this is what we have. And, it just needs to be rewritten and updated because there's, the last time it was updated, I think it was last year. So we've done a lot of work this year. And actually, I don't even think I properly updated it with respect to Himanshu's work. But anyways, I'll work on that too. But yeah, it would be helpful, Sarrah, as if you could put together like an outline of how you might envision how we would test the model, how we would implement tests of the model. So, if you have specific ideas of things that you want to look at or test, that would be great. We also, I don't know how much work you've done on like reviewing like some of the tools involved, like, of course there's agent-based modeling, but there's also like large language models. We did the paper in the meeting on reviewing large language models for social simulation. There are other papers that are probably relevant there, and kind of walking through those, what they've done, and then how we kind of have either taken from that or differentiated ourselves from that. And then we get into the models, showing the results. And then that's pretty much it. We write a conclusion, and that's the paper. So I like to make this, kind of break this down into steps, because a lot of people are pretty overwhelmed by thinking about a whole paper. And it's really, just thinking about what you want to accomplish. There's probably stuff you already have that you can pull into the paper. And then after that, it's just a matter of putting it together and reporting everything out. So yeah, let's make a kind of a long-term plan for that. But the first thing we need kind of is an outline of what exactly you want to look at in terms of running the model, having those experimental conditions, and testing them. So it's kind of hard to do. We have kind of limited computational resources. So if we're working on LLMs, it's going to be a little hard to get good, robust tests. But I think just kind of showing some simple examples are good. So don't think, that we need to have like this super, super high-powered example. Just having some, basically easy to digest problems. Because you want to make it easy for people to see the implications of it as well. It's not just about like, overwhelming people with data. I know a lot of papers, they try to do that, where they try to like jam as much data into the paper as possible. But that's not necessarily a great strategy. Do you have any thoughts about that, Sarrah?
Right. Yeah. So, so like by examples, you mean like, so like I took the calculator project as like example task during my research. So you mean like a few more of those, right? It should be easy to see and like how it's progressing during the simulation, something like that.
Yeah, so the calculator task would be a good example. And then of course having things similar to that. So you might have like a simple video game, or maybe like a app that, I can't think of anything right now, but they're very simple.
No, I'll definitely try to like, sit and think on some like around 3 or 4 like more simple but like still doable and like that can be seen, like the progress of which can be seen throughout the simulations. I try to think of like 3 or 4 more such examples. Definitely. And then like the test conditions that you were talking about, so those would be something like whether all the agents start out at like a very high experience level or low experience level. So things like that. Or like, are you talking about something else entirely?
Yeah, so you want to have like, if you have different tasks, like say you have a calculator task versus like you want them to write like a short story. And like, and I know that's a little bit outside of, well, it's not really outside of open source. You could open source a short story. Having like maybe different types of skills applied. And then in the project, you would have like, you'd set like the calculator at a high skill level, the calculator at a low skill level. Or you could have everyone at a high skill level mixed and everyone at a low skill level, and then do that for the short story. And then right there, you have 6 conditions you can test. And all it is just rerunning the code at different settings, but making sure that you have things you can compare. So like if you want to compare high skill level, different types of things that they're doing, low skill level, different types of things that they're doing, and look at how it performs in that range of things. The key is sometimes to have controls. So, you have like, you keep things kind of constant, and then you make a comparison of one thing. You vary one thing, which is maybe the task type. Everything else is held constant. You then take those things that are held constant and you change them all together and you look. So you can kind of get a sense of, if the task type is the thing that the model is, maybe it does well on one task type, it doesn't do well on another task type. Or it does well when every agent has a high skill level, but not when I have a low skill level. Things like that. So at the end of the day, we can make those kind of judgments about it.
Like, as you said, like the first task is like trying to make an outline. So I'll try to do that once, and then like once I've done that, I'll get back to you for like more insights.
Yeah. Yeah, that's good.
Sure.
All right. Thank you.
Thank you.
All right. So that's good. Do we have any more updates before we move on, or any other comments?
I could say a few things.
Okay.
Depending on what you wanted to say today, there's more. I've been writing sort of a post about teleology. Well, I'll start before that. I'll finish with the other thing. The ICOR meeting. It was interesting. It was for open research, and the topic was meta-science, and I didn't get to see all of it, but I was there, and I have a few contacts at both ICOR, but also I think that is based in the Center for Open Science, but the Meta Science Alliance itself is this new attempt at having some kind of a centralized effort, because like meta science across different fields have their own particulars, and there's a lot of doing open research in one field versus doing open research in another, and trying to be interdisciplinary. There's a lot of different complications to it, and I've been in and around the space, but like at an actual like bigger level of the Center for Open Science, the ICOR, and other groups like that, and their projects. Like I'm not really that familiar with them, so it was just interesting to see kind of what people are doing in that space. There's also someone at Virginia, I forget his name, that was asked to help out with certain things from a data science perspective, which is really interesting for me to see I can't pull up his stuff and remember his name, but he was used with, I think iCarly worked with him to do some basically data science, meta science work that was interesting to me. So I'm actually going to look into that more because I've been trying to figure out, like, okay, what can I do with quote unquote the data science stuff that I'm learning, to be very casual in speech about it, to these ends. So I want to look more into that space. That's hold on, actually I need to do this first. Outside of that, we've had a lot of discussions recently on the 1943 paper, and the one on purpose behavior and teleology. And it's been a very interesting touchstone or reference point, because in the last Cognition Futures meeting a week ago, we went through it, and then we also there's been a lot of different contexts for it. Like Radley's kind of gave a few different raps on what were the contexts and sort of the pre-microbiology context, but also we talked about Maxwell's demons, and I've actually spent some time this weekend looking into a much broader arc of it. It's actually made me a lot more interested in reading and Kant and what the response to intelligent design and the watchmaker stuff. And then there was stuff before that, and it's actually a really interesting lens for me to kind of look at a lot of philosophical content in the past that I've not been interested in at all dealing with, just because it was, I don't know, it's been a very interesting lens to kind of put into these big huge things. Obviously teleology goes all the way back, but seeing the different incarnations of it evolve during the Middle Ages or medieval stuff, and then getting into actually getting into the Age of Enlightenment and the scientific revolution before that, and how things, what the battlegrounds were, was an interesting space. And I've written some things to condense that for this smaller post that I'm writing, but I'm kind of wondering in the future, I might, what's sort of the actual story that I want to say about that that's been on my mind a bit, because in one sense, and I kind of want to look a little bit more into it, it's sort of one thing to say, okay, it's a 1943 paper where our three heroes are going against the grain, against the sort of recent disinterest in discrediting of purpose, but it feels like that's an underselling of what's happening, both in a broader sense too. It's not there's a lot going on, and it's not like they're not just, and Bradley articulated this very well in the last meeting, so I'm probably not doing, I'm not trying to do his comments justice either, but just understanding that space and kind of the separating out of non-mystical teleology away from that, and what does that mean for this other stuff. And I feel like there's something to really go into in terms of all of the recent, some of the recent people we've been looking at. I haven't gotten to this part yet, and this is something that I'd like to talk more about in one of our non-Saturday meetings next week. But even returning to Thomas Fuchs a little bit and his ecology of the brain stuff, and his his take on like, okay, yes, anti-reductionism. The paper itself comes up in Levin's work all the time, and he's sort of dealing with this sort of agential material stuff. What is, that's a whole, I guess, modern biological heavy take on it. And then you have David Krakauer, who kind of started this thing off with Bradley mentioned the Complex World book and the talk around it. So it's kind of I see this in what I'm putting together. I'm seeing this like going into the actual contemporary people and these issues, looking at the stuff and in these different fields. And I actually think there's something also about meta science to be said here too, or some of the broader efforts there. But I haven't quite figured it out yet. I was hoping to submit this just to the medium and not basically just to Bradley too, because I think Bradley will want to say some things. But I guess where am I coming to with all this is sort of saying, okay, there's a post to be said about the paper and our discussion for it. And I've already mentioned something that there's a longer project with David Krakauer's particular take on complexity science, which I don't really even know how to properly frame yet relative to other things, because I don't think I'm sure that everyone in the complexity space doesn't see things the way that he does. But I find myself on this path of trying to investigate some of that stuff. And yes, like the philosophy of history stuff and the history of quote unquote science and the history of geology is a very interesting space. And I don't really want to spend a whole lot of time there, but I feel like I'm in the process of getting this broader inertial understanding that was exciting this week. So bottom line, I think I will still try to submit a somewhat smaller thing, but it kind of gets as I'm writing it, it's like, okay, should this become an appendix or should this become a different, like a paper altogether? Because when you get to like actually broader sense of teleology and all of the stuff, and like there's some things that you just don't want to get into, going further back, and like there's obvious things that like, yeah, we got to stay very, 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 very reacclimating to the sense of what all the baggage that it has is another way to think about it. I still plan to send that hopefully today in at least an abridged version, and then when I show that, I wouldn't mind a discussion with Bradley or maybe other people in next week too. But just like what ideas for future works based on where we go with that, and I know things kind of dovetail here with our efforts in other cybernetical things we want to do. So I think maybe kind of maybe part of the next cybernetics reading group meeting. I don't think Amanda's here, him or good. I think part of the next meeting, maybe either Wednesday or Thursday meetings, let's say. I think there should maybe be a little bit time spent on one. I kind of have my vision for where I want to go with things, and I'll just go there on my own. But also like what I guess offering relative to what I'm inclined to do. See what if people want to do anything further in those spaces, I suppose, and what they have in mind for how to either read stuff or do make some materials on it ahead. So that was. Any questions about that? That was pretty unstructured, but
it's fine. Yeah, it's great. Thank you. I look forward to reading the blog post. And yeah, I've been kind of interested in this topic too. I think, we're going to talk about that in the active presentation, but I think there's a lot more to say about that. And I have some notes on it myself, so we should kind of merge things together.
Yeah, it's one of those things where I found myself surprised. I think that's a fair way to say it. Surprised in the sense of, oh, there's actually a little bit more here that I feel I want to get into, and also would be good to understand. Like even outside of I don't know, not just the historical stuff, but I think the historical stuff is more like there's much more at play than I guess I originally understood in some ways. So that's cool. And then also like again going into the actual modern like Fuchs, Levin, and Krakauer, like there's something there, and I don't know what yet, but yeah. Anyway, yes, we'll talk more about that ahead. Other stuff happening. We didn't have our regular meetings this week. I think next time for the cybernetic, well, in the reading group, or one of the reading groups, we will be looking at the Bergson memory paper. I know Amanda was interested in that, and that's on the top on the agenda. I looked a little bit at that. It was quite interesting, kind of about where our memories, what our memories, stuff like that. If I'm remembering that right, and I was looking at another video from Levin a while ago, which I think also came up again with the Rosenbluth, I don't know what to call it, chart, tabulation table, where they select from prediction and then higher like various orders of prediction. But like getting into why they selected for prediction, why they're trying to differentiate teleological stuff, why they're trying to lay this groundwork for like an assessment level, a way to assess both like natural and artificial behavior, and where they were in that process and what they can see from there, and so on. So, but yeah, interesting stuff. We'll do that next week. I will be. I guess the easiest way to say is traveling a bit next week, but I should be able to make our meetings as usual. But I'll say more about that as it comes up. But that's I will return the mic to you, Bradley.
Okay. Well, thank you, Jesse, for the update. Looks like Morgan is wanting to say something.
Just one, I thought that the Krakauer lecture was particularly funny when he was he was talking about the different definitions of complexity science, right? And then I think he read out Varela's, or someone associated with Varela.
Yeah.
He read out this portion, and he was just like, I'm not sure that's helpful. Or like, I'm not sure that cleared things up.
Yeah.
I forget the way he put it, but a lot of good, a lot of great material covered there, and I wasn't sure, if we wanted to make that a focus or wait for the book, or is the book available?
Oh yes. Yeah.
He said he was signing. Oh, okay. So okay,
it's like $6. So
okay.
I actually almost ordered a second one because I'm somewhat notorious for having books. I mean, everybody, I click books, I don't read them, haha. But like, I really don't. I don't physically enjoy having a physical material book and reading a physical material book. Most of the time. So it's kind of funny because I actually decided to physically hold this book. Also, there's certain things that the SFI is doing is like, it's like license cost restrictive for us to sell. We can't give you a PDF of the book. So this is basically what it comes down to. So like I bought it's super cheap, but like I bought the physical copy anyway.
Yeah.
And then I lost it for a bit, and then I found it again. So
is it called Complex Worlds?
Yeah.
Yeah.
But outside of that, yes, that's what the book is. And it's nice because it has well, I think it's a broad overview, but then I'm also curious to find there are other books on the foundational papers, because apparently those books are like, they'll have like Maxim Roginski going through a contemporary person looking at a topic, or someone looking at the Arturo paper, someone looking at these modern complexity scientists looking at these foundational papers. So that should be fun. I haven't really seen anything on them. I don't like, the commentaries are yet. That should be good. Outside of that, I realized I kind of blabbed this all over the chat earlier this week, and I forgot about it until just now. I think we're familiar somewhat with the Stanford Institute and the Complexity Explorer, and they had a complexity podcast for a while. And it's quite funny because I found out about it a while ago, and I don't really know what to make of it, and I didn't get into it. But I was loosely following Michael Garfield as the lead of the podcast on back when I used Facebook more, which feels like a long time ago. But he would post there about it, and I'd see updates from Michael Garfield. I don't know if I was friends with Michael Garfield or whatever. But for some reason, I remember getting these updates a long time ago. Suffice to say, I found one of the earlier podcasts. I think the Complexity Science podcast has changed, or Michael Garfield isn't hosting anymore. I don't remember. But there was this one, David Krakauer on the Landscape of 21st Century Science is the title. But it was very interesting, and I think I would actually like to. I guess it could feed into our talk on open science somewhat, because part of the discussion there is not just about complexity, but how science has changed over a while. Like the kind of we're a little bit familiar with the lab now about the efforts against reductionism and why reduction went the way that it did, and the usefulness of it, and the importance of it, why it went this way. David talks about his role as kind of shepherding this small group of people in Santa Fe in the mountains or wherever that aren't beholden to what kind of risks they can take. They can't take a lot of financial risk because they don't have the money for it, and then whatever, but they can do certain ideational risks. They can do these, they can have certain discussions that are harder to have, and they're very kind of stuff that felt a little bit nice, or a certain kind of brotherhood, if you will, with some of what orthogonal does, in the sense of we have the kind of risk that we take and don't take, and why, which is maybe a strange way to phrase everything that's happening, because we don't like to talk about risks here, but the nature of guiding people through interdisciplinary work, and then how he offers spaces for them to grow, and then eventually potentially leave the institute to do this stuff. And how does that fit with complexity? How does it fit with science? How does it fit with what kind of ideas and things you're working with? It was very interesting, what he's doing in the lab, and how that fits with the broader landscape of the 21st century of science. And the opening, I think even the caption is the opening line of the caption of the podcast or whatever is, for 300 years, the dream of science was to understand the world by chopping it up into pieces, and kind of goes from there into the mechanism or reductionism and stuff like that. It's okay, it's just a nice I don't know. It's a very interesting talk. And in the talk, my last thing I'll say about it was, there's Michael Garfield, I think, referenced Varela and Unbecoming Aware, and sort of the different components of doing research, or getting an idea, and having it as an idea at its inception, and how that's the very first person moving from me towards second person stuff and trying to get a dialogue about it, and then getting third person into the world in different ways. And it was a funny a pleasant reference that we're familiar with from stuff. So it was an enjoyable discussion. But I will leave it at that. We can talk about other stuff now. So
Okay.
I think it's interesting. It's not available at Powell's Books, but it is on Amazon, of course.
Yeah.
I didn't find it in some local places here either, which is
Okay.
tough. But it's also new. But I think it's also like kind of limited.
Yeah.
We live in the age of the Borg. Wanted to, well, I have a further update. It's not totally relevant to this, but but you brought up Levin just a bit ago, and the Cortical Labs Journal Club, Cortical Labs is this startup down in Australia that is doing, let's not call it organoid intelligence, dish brain.
Yeah.
Dish brain as a product. And they just did the Brain Aware paper from Indiana. But are talking about doing the Michael Levin TAME paper next.
Okay.
So wanted to advertise that because it would be it would be cool to potentially show up for those who could and represent with a group of people that are definitely like organoids, intelligence interested. But anyway, just wanted to mention that.
Oh, well, that's good. Yeah. I don't know if you have like links for that or what.
I'll get links on. Yeah, for sure.
All right.
I just saw that they had they don't have a date yet. It would be probably like a little after mid-October.
Yeah. Yeah. So, I think we should have like maybe more of an explicit sort of complexity kind of focus, or do things that are more in sort of forward facing in terms of complexity. I mean, we do things, but it's kind of like they're not really advertised as such, or they're not really thought of as such. So I think that's very good stuff. I think also, having this connection between open science and complexity science, that's also another thing that maybe we could look at for this event with Act Inference, because they're interested in complexity theory. It's not, again, like, in our case, it's not really that forward facing. So they're doing a lot of things in that space, but it's kind of like, how do we make it sort of, I wouldn't say like exactly like the Santa Fe model, but I think the Santa Fe model has been somewhat effective at like public consumption of complexity and tying that to maybe, well, I don't know if they don't really do a lot of open science, at least explicitly. They don't have like a lot of tools that they build and put out in the world, but you get the ideas, and that's the kind of direction you want to go, because so that this is something we should talk about more, in the coming weeks. We're in Slack.
Yeah, I mean, I think that's actually particularly interesting. I mean, I think one of the reasons that they don't is that they don't. That I mean, I could definitely imagine speakers coming, and I can think of a few people who've spoken and are potentially like external SFI faculty that have talked about some of those relationships, but or like relationships. But I think it's also just, like they somebody just needs to draw those connections for them. Just thinking about in particular, I think maybe it was like how he was introduced by Jeffrey West, as like David Krakauer's thing is following, what do they say, like following the kind of the different means of intellectual pursuit or organization. I forget the way he phrased it, but it made me think of actually the most recent work of oh God, this is my professor from like 1993, Mark Badeau, right? So early A-life researcher, right? Like I think he had something in the 2000s where he was doing kind of like analysis of U.S. patents.
Oh yeah, I know that paper. Yeah.
It's together with somebody else that I think was like down in Santa Fe, but not necessarily SFI. Anyway,
yeah, it's a Santa Fe
together
thing.
with
Yeah.
But you know what I mean, like it's. I mean, this is what makes complexity science so hard to define, right? It's like it could literally be almost anything. Right? It's about drawing the connections. It's about as well as having the data, or like having an interesting data set, or choosing an interesting perspective on data. Anyway, I think that would be cool to think about the like how would SFI think about software or software communities and their relationships, and especially in open source. Just thinking again, like about the kind of the Linux community and the Linux community of the greater Linux community of tools, and how they share and how they divide up, kind of how they create their niches, and how they interoperate, etc.
Yeah, I actually cover some of that in my project management class, but I don't have like a complexity. I don't have an explicit complexity theme or lecture. I guess I do have a lecture on complexity, but there's a lot of complexity stuff in there. It's like there's a lot to say about that as well. Like I think like the Linux space is a really good example because there's so much going on that you could, if I don't know where if they have data on things, or if you have to sort of collect it from.
They do, or like I can certainly think of smaller perspectives where people just look at like kernel development, right? Because they've got this massive history data set, as well as like the communication surrounding it in terms of the mailing list and things like that. But yeah, definitely interesting area.
Yeah. All right. So yeah, thanks for that discussion. I think that's something really interesting that we can follow up on. Talk about. All right, I'm gonna talk about HyperNEAT and some tools associated with it. You know what it is.
Cool. Yeah.
All right. So it's not like an obsessive compulsive person. It's a platform for doing evolutionary computation and some neuroevolution stuff. So this is HyperNEAT. It's a platform that was developed by Kenneth Stanley and colleagues. So this is the Wikipedia page. It's hypercube-based NEAT, or HyperNEAT. So NEAT is the neuroevolution of augmented topologies. That was developed by Kenneth Stanley. And HyperNEAT, or hypercube-based NEAT, is a version of NEAT. So HyperNEAT is a generative encoding that involves artificial neural networks, or ANNs, with the principles of NEAT. It is a novel technique for evolving large-scale neural networks using the geometric regularities of the task domain. So it's this sort of geometric approach. We've talked about information geometry before. It's kind of consistent with that. And when you're talking about hypercubes, you're putting it in this space that's, allows you to build this binary hypercube and then watch things evolve in that space. So I don't know if we're going to have an example of it here, but basically that's what they're trying to do. They're using these agents that have evolving artificial neural networks, and they look at how they sort of evolve over time and examine that process. It uses compositional pattern producing networks, or CPPNs, which are used to generate the images of Picbreeder.org. So this is Picbreeder here. I don't know if it's still online. We'll see. Okay, I don't think that's online. So Picbreeder.org. And there are other things like endlessforms.com and things like that. HyperNEAT has recently been extended to also evolve plastic ANNs and to evolve the location of every neuron in a network. So this evolving the location of every neuron in the network, that sounds like something that might be useful for credit assignment. That is Sebastian Ricci and Kenneth Stanley. An enhanced hypercube-based encoding for evolving the placement density and connectivity of neurons. That's actually in the Artificial Life Journal. That was in 2012. So that's, kind of thinking about sort of, how neurons are placed in a network, and looking at this hypercube-based encoding. So this is the thing that they're using in HyperNEAT. Then also, CPPNs are compositional pattern producing networks. So this is where they take an artificial neural network and they evolve it using genetic algorithms, different versions of genetic algorithms. And then this paper here associated with that is by Kenneth Stanley from 2007, Compositional Pattern Producing Networks, a Novel Abstraction of Development. So this is actually going back to developmental biology and the programming of developmental systems and things like that, basically trying to develop a network. Genetic Programming and Evolvable Machines is the journal, and that's from 2007. So this is basically, kind of the very quick overview of things. They have a list of applications: multi-agent learning, checkers board evaluation, controlling legged robots, comparing generative and direct encodings, investigating the evolution of modular neural networks, evolving objects that can be 3D printed, evolving the neural geometry and plasticity of an artificial neural network. So there are a lot of applications to that. Actually, let's look at this paper if we can. So this is the original paper by Ken Stanley on compositional pattern producing networks, a novel abstraction of development. And this is a Genetic Programming and Evolvable Machines. This is a journal that does a lot of stuff, publishes stuff in genetic programming and genetic algorithms. There's a whole taxonomy of approaches related to like genetic programming and genetic algorithms. Basically, evolutionary computation is the larger category. So, we talk about these different methods. They're just very specialized versions of evolutionary computation. So the abstract reads, natural DNA can encode complexity in an enormous scale. So they're looking at this sort of encoding of a chromosome or a gene using, binary strings or other types of structures as sort of artificial DNA. Researchers are attempting to achieve the same representational efficiency in computers by implementing developmental encodings. So this is where they're kind of coming up with developmental encodings. And when they talk about developmental encodings, what they mean are encodings that map the genotype to the phenotype through a process of growth from a small starting point to a mature form. So they're looking at this, like they're trying to develop a map of taking like a genomic encoding or an encoding of the DNA, mapping it to a phenotype. It could be a one-to-one mapping. And of course, in biology, we know that's not really the way it works. It's a multi-to-multi encoding. Anyways, they're just trying to map some representation to something in the world, like a phenotype. They're using growth as maybe their starting point, and they basically can grow things in that way. A major challenge in this effort is to find the right level of abstraction of biological development to capture its essential properties without introducing unnecessary inefficiencies. So this is basically where they're trying to find the way to kind of transform things developmentally. It's kind of like what we're doing in some of the work in Dev AI. And, this is kind of the standard approach for, because obviously you want to get down to the genetic level. You want to have this kind of genotype to phenotype map, and then you want to be able to differentiate things. I think the way we've kind of done it is to not focus on growth as much as transformation, but this is just kind of different ways of doing this. So in this paper, a novel abstraction of natural development called Compositional Pattern Producing Networks, or CPPNs, is proposed. So this is where they're actually wanting to put patterns together in a growth. So this, and the network's producing these different patterns, and it's just composing different aspects of it. Unlike currently accepted abstractions such as iterative rewrite systems and cellular growth simulations being something, like some of the platforms that we've talked about in DevoWorm a lot. And so that, that's one way to do that. You also have these iterative rewrite systems, which are basically introducing, variation into the process. CPPNs map to the phenotype without local interaction. That is, each individual component of the phenotype is determined independently of every other component. So this is where you have so let's map this out. So let's say you have this little organism here. That's like 5 limbs, maybe a gingerbread man almost. And then you have this genotype to phenotype mapping. And the map is just simply taking a series of strings. All right. And these could be binary strings. So these are 0 and 1. And then those binary strings map to some set of features in the phenotype. So this is phenotype, this is genotype. And the phenotype is here, so we might have this gene here mapped to this limb, this gene here mapped to the limb over here, this gene here mapped to this leg, this gene mapped to this leg, and this gene mapped to the head. Okay, and it's just ordered in that way. It's a very simple map. It's more or less correspondence. So if you have this gene, it maps to something. The features of this head are all encoded in here. And of course, they all are independent. So you can knock out this gene and knock out the head, and you would just have not a tetrapod anymore. You would have a headless gingerbread man. Where you could mutate this gene in different ways and change this part of the phenotype. Okay, so it's compositional in the sense that it's pulling together, it's kind of like if you were to pull together all these parts and you were to express these in development, you would get basically this form, but these operate independently. So you can knock one out and have just 4 limbs instead of 5. There's no interaction between these genes. It's just that these are modular. So the genotype is, modular. And, you put the pieces together. So you put 1 plus 2 plus 3 plus 4 plus 5, and you end up with your phenotype. If you knock out 2 and 4, you end up with a phenotype that has 1 plus 3 plus 5. and so on and so forth. The other thing is you have the phenotype developed in pieces. Now in biology, of course, a lot of times you have things that are linked. So like, your limbs might be controlled by, say, like a Hough gene or something, and then that controls the expression of other genes. So you might have the genes maybe for the forelimbs, for the forelimbs here, for the legs, and those are different genes. So this would be forelimbs, this would be legs, this would be the Houghs, which would just sort of regulate the growth of these. You don't have that in a CPPN, but it's basically compositional. And if you're looking to build something that is, modular, highly modular, then that's what you kind of want. So results produced with CPPNs, they're interactive evolution of two-dimensional images. And so this is where we go back to the Picbreeder stuff. And I'm not sure if people have ever seen one of these, but it's basically a platform where you have, like, you give it a bunch of images, you train the model on a bunch of images, and then you generate a bunch of images from that, and then you select the images that you find interesting or beautiful or whatever, and then that's acts as natural selection. It then generates more images, but on the basis of the thing you selected. So eventually you can keep selecting for images, and you get this subset of images that kind of goes in the direction that you're selecting for. And so this is how CPPN's gonna take this phenotype and like refine different things in it and build from like primitives and give you sort of this, this sort of thing of high fitness. In this case, fitness being beauty, but you could do this with actual phenotypes. A lot of robotic control problems use this, etc. Results produced with CPPNs through interactive evolution of two-dimensional images show that such an encoding can nevertheless produce structural motifs, often attributed to more conventional developmental abstractions, suggesting that local interaction may not be essential to the desirable properties of natural encoding the way that it is usually assumed. So that means that we don't care about local interaction so much. We have these structural motifs that are important. These primitives that are kind of, based on, the components of a phenotype or the components of a problem space. If you think about this in terms of a problem space, you might have hypercube, just, if we look at it like this, it's kind of like a three-dimensional square, but we're just looking at sort of the skeleton of that. So we have nodes that kind of are like this. And then we have a cube nested within that cube. So we have a cube here. We have like connections here. It's kind of hard to draw because it's like you have this, drawing a nested cube is hard. But we'll do this real quick here. Get to the point. It's basically just kind of like this, a cube within a cube. Okay. So yeah, I didn't draw the back of this cube here, but anyways, we have a lot of things going on here. And so each of these nodes have like a value. So it could be like 4. I don't know how many we have here. But the idea is you're trying to go from this initial point to this endpoint. So you're trying to, say, introduce mutation at each of these steps that give you like kind of a mutated phenotype. The phenotype being binary values. Actually, that would be the genotype, but the phenotype would be kind of the route that it takes through the hypercube. So if you give this initial condition or zeros 2 mutations, you end up with this state of the genotype, and you end up with these edges as the phenotype. These states as the genotype, and you end up with these edges as the phenotype. So you can actually map out the phenotype that way, and then put together phenotypes to build a whole, a phenotype, compositional phenotype. So, yeah, this is kind of the basis for NEAT and HyperNEAT. And so HyperNEAT uses hypercubes, but they use it in a different way than what I was just showing. So, there are different references here. This is another reference by Sebastian Risi and Kenneth Stanley, indirectly encoding neuroplasticity as a pattern of local rules. This is in From Animals to Animats 11, which is a conference proceeding from a conference called From Animals to Animats. Now, next thing I want to talk about here is that we have a series of GitHub repositories that have HyperNEAT involved in them. So there are a lot of ways you can implement HyperNEAT. There are tools in TensorFlow. There are other types of libraries for HyperNEAT where you're combining it with other types of approaches. You have Deep HyperNEAT, which this is developed by Felix Sosa and Kenneth Stanley. It's based on this paper here. You have all sorts of different, you can actually implement SharpNEAT in Unity. There's UnityNEAT as a project, so this is kind of interesting that they're using, it kind of intersects with Unity and some of the, three-dimensional modeling that's going on there. The implementation of evolvable substrate HyperNEAT algorithm in Go. So this is where we have ES HyperNEAT being an extension of the original HyperNEAT method. A lot of things here that, if you're interested in applying this a lot of people are doing this to develop actual brains for like robots and things like that. So this is actually the neuroevolution knowledge base. This is someone's take on neuroevolution research. So there are a lot of resources here. One in Julia here, Deep HyperNEAT in Julia. So a lot of resources here for people to look at. I can put this in the Slack for people to go over. This is a Medium post, HyperNEAT approach and evolution. This is where they talk a little bit about HyperNEAT, basically extending the capabilities of evolutionary computation, particularly in evolving artificial neural networks. HyperNEAT stands out for its ability to harness geometric regularities in network topology, paving the way for evolving large-scale efficient neural networks. So HyperNEAT is really focused on evolving neural networks. The neural networks then serve as the encoding for some phenotype. So what I was describing was kind of a general genotype to phenotype mapping to some geometric phenotype. Now in HyperNEAT, you're actually using the nodes of the network and you're evolving that network, and then you're producing something from that network. This article delves into the intricacies of HyperNEAT, exploring its foundational principles, operational mechanics, and its impactful role in the broader context of machine learning and artificial intelligence. So they talk about neuroevolution being a subset of evolutionary algorithms focused on evolving neural networks, and how those in turn have evolved from simple structures to complex architectures capable of tackling a myriad of challenging tasks. The introduction of HyperNEAT marked a turning point in this evolution, offering a novel perspective on how neural networks can be developed and optimized. So let's see. So the foundational concepts are that the HyperNEAT approach is an extension of NEAT. The NEAT algorithm was originally designed to evolve both the topology and weights of neural networks. So they're actually mapping their genotype to their phenotype, which are these topology and weights problem in neural networks. The crux of HyperNEAT lies in its indirect encoding mechanism, which uses a compositional pattern-producing network, which we saw in the foundational paper for, to encode connectivity patterns of artificial neural networks as a function of geometry. So the phenotype really is embedded in this geometry, in this geometric space. And that's really kind of one of the key points, is that there is this underlying kind of metric space or geometry. This approach allows for the efficient representation of large networks with inherent regularities such as symmetry and repetition, which are often observed in natural biological networks. So, you have these networks, these neural networks that have these regularities, symmetry, and repetition, and you'll see this in brains as well, with the placement of neurons and the neural structures that result from, morphogenesis. So it's interesting. Compositional pattern producing networks are a form of artificial neural network. Unlike traditional neural networks, CPPNs are not designed for tasks like classification and regression. I think this is an important point. Instead, they are used to generate patterns and structures, which can be applied in various domains. So CPPNs are exclusively generative. They are not, they don't really produce classifications per se. They just produce these patterns, and then, you can do things with those patterns, put them together into larger things, and, take those motifs, build up, you have repetition, you have symmetry, you can build things with it. These patterns and structures can be applied in various domains, especially in evolving the topology and weights of artificial neural networks. At their core, CPPNs are inspired by the processes of natural development and morphogenesis, the biological process that governs the shape and form of an organism. They use a composition of mathematical functions that create complex patterns. These patterns can manifest in various ways, from symmetric structures found in biological organisms to intricate designs and network topologies. The structure of a CPN resembles that of a standard neural network, consisting of nodes and connections. However, the key difference lies in the diversity of activation functions used in the nodes. So ANNs might use a single type of activation function across the network. So you might pick ReLU or sigmoid, and that's your activation function for the whole network. CPPNs, by contrast, employ a variety of functions, such as Gaussian, sine, cosine, and sigmoid. This diversity allows CPPNs to produce a wide range of output patterns, depending on the inputs and the arrangement of these functions within the network. So you have this diversity of different activation functions, presumably mimicking like how different types of neurons exist in the brain, and they have different activation functions, and they produce different types of outputs. So this is, kind of a way to kind of evolve kind of brains in a modular way. Basic compositional pattern producing networks in Python involve defining a network that can generate patterns based on its input coordinates. So you need to have, implementing this in Python, and they have the code here, you define a network that can generate patterns based on input coordinates. So you have this example in Python of a CPPN. This example will create a basic CPPN and use it to generate a two-dimensional pattern. So you have this class CPPN, it kind of goes through this. You're importing, I think you're using NumPy, and then it uses this class. You have a function here for activation, so or you have a number of activation functions here. Basically, it's walking through the different activation functions, and it's choosing from 10H, Sin, and Gaussian. So you have these different activation functions, or if none of those fit the data, then returns linear, return X. And then you're another function where you are defining the activation functions and doing that. And then you're creating the CPPN, input size, hidden layers, output size. Create a 2D pattern, would generate a 2D pattern on an array, and that's what we're doing here. And then we plot it out. So this is what it looks like. Generated pattern by CPPN. You have this gradient of color from yellow to blue. And you can see it's like kind of a color map, a nice pattern there. And so this is generated all from this neural network that has different activation functions and can just put out this phenotype on this two-dimensional array. So this is a two-dimensional NumPy array. So this is not a very simple phenotype. It has components that you can look at and say these could be modular. You have an area of blue, you have an area of yellow, And these are all produced by these different activation functions, this variation across the gradient here. If we consider this array as an artificial neural net spatial substrate pattern, I don't know what that means. So each element could correspond to the weight of a connection or the activation of level of a neuron in an ANN for specific spatial coordinates. So basically, I guess there are ways to do spatial correspondence in artificial neural networks. And it's basically kind of what the CPPN is doing. So we can make a 3D visualization. And, we have another example here where we output these different points in space. So we have this three-dimensional cube where we plot out all these points. It's basically, visualizing an artificial neural network based on this CPPN pattern, because we have these, features in here that are ordered. We can actually plot this out as a scatter plot instead of a gradient, and we can get this. So basically, we're iterating through the grid and plotting neurons with the output above threshold. So basically, these are all the active neurons in the CPPN network, conforming to the pattern we saw in the first example as a three-dimensional scatter. And so this is where we have our points. And you can see they're highly ordered in space. And so that's what we have there. So each blue dot represents a neuron in the artificial neural network. The x and y coordinates for each dot corresponds to a neuron's position in the two-dimensional substrate. And then the z-axis represents the outputs of the CPPN for each neuron, indicating the strength and nature of the connections from that neuron. So this shows how CPPNs generate a pattern of connectivity across the neural network. Neurons with higher or lower CPPN outputs are more likely to form stronger connections, as indicated in their position on the z-axis here. So they're kind of segregated out. They're either high or low on that axis. This 3D view provides a more intuitive understanding of the spatial distribution and connectivity strengths in the ANN as determined by the CPPN. So this kind of goes through this. Now, the last thing I want to show for this is this substrate designer. So you can actually create substrates for HyperNEAT and then import them into HyperNEAT. So basically, this is a nice tool for this. You can place nodes in this three-dimensional space. So why don't we place some nodes here? And you can actually do this with a pattern of whatever of your choosing. This is just designing the substrate like that. And then you can place or remove input nodes, place or remove output nodes, which might be the ones down here. Okay. So you have input nodes, output nodes. Now I want to create dense connections. So finish dense connection. So I don't know why it's not doing it, but yeah. And then let's try this. How about input nodes here? Okay, it's not doing it the way I had it before. But it's basically creating a couple of things. It's creating input nodes in position this two-dimensional array. It doesn't have any hidden nodes, and it has these output nodes in red. And then it's not defining any connections because I don't know why. But then it should, connect these together if it's working properly. And then you can define a layer and finish a layer. And then you basically can design this in a visual way, get all the coordinates here, and then you can export the substrate as a JSON file. And the JSON file has everything encoded, all the positions, and it has, the annotations, and then you put that into HyperNEAT, and you can use that substrate to do your computations. So that's just kind of an overview of HyperNEAT and some of the connections with not only artificial neural networks and pattern formation, but also this sort of developmental AI aspect. Okay, Morgan, you had some links in here.
Yeah, the first one. So as soon as you had Picbreeder up, it made me think of the most recent machine learning street talk, which again is my a favorite YouTube channel. The researcher that they are talking with is also focused on open-ended AI. So he's very much, he's got some projects that are kind of like building on or certainly inspired by Picbreeder and Kenneth Stanley. Yeah, Kenneth Stanley's work. And then I dropped a link of what I thought was perhaps someone who's recreated Picbreeder, based on the old website. Like, because I think Picbreeder.org has been down for a while.
Okay.
And yeah.
Oh yeah.
But
So
super cool, and it's I forget which was it, the CPPM paper that was 2007. Anyway.
Yeah.
I was just I was having a moment there, thinking back to
2007. Yeah.
I was like, what was I doing back then?
Yeah.
And so yes.
Yeah. So this is. Yeah, and I mean, we haven't talked, I don't know if we've talked too much about neuroevolution, but like there are a lot of interesting things. So you can do like the Picbreeder stuff with, a regular genetic algorithm. So this is the Picbreeder site. This is where, you can do things with all sorts of evolutionary computation with genetic algorithms. You can even do this with an artificial neural network. And you might ask, why do you care about evolutionary computation and this sort of thing? So, one of the things you can do, of course, here is that you're not trying to classify images. You're trying to generate new images from like sort of a database of primitives or a database of images, and then apply natural selection to those images to find kind of an optimal solution. But you don't know what the optimal solution is until you kind of select for it. Go ahead.
Yeah. It became a kind of interesting, like Galaxy Zoo. It became an interesting, crowdsourced, wait for a sighting, kind in the spirit of like Wolfram's, cellular automata, where it's just like on the basis of these simple rules, when do you see complex again, you're not sure what you're looking for, but you know it when you see it.
Right. Yeah, it's
that old rule.
Yeah. I don't know if you can actually do a demo here, but it's basically, okay, so new user, if I want to start evolving.
Yeah. That was a quick, yeah.
So I might do a mutation. And let's restart. Okay, here are a bunch of images. Let's mutate if it's working. And then, I can save it. I don't know why it's not working the way I would. I guess I have to select one, or
maybe
do that. Well, anyways, the idea would be you have these images, you mutate the images. Okay, there we go. Mutate. And then it mutates them. And then they keep mutating, and you get variants, and you select variants. And you select a variant, you mutate that variant. So let me select this one. And you're mutating it based on the thing you selected. So it's creating new variants from the one you selected. And then you keep selecting, and eventually, you might end up with something that's really interesting or desirable. So you see I'm shifting this fitness landscape. I'm exploring different parts of it. If I have this purple picture up at the upper right, I mutate that. I end up selecting for sort of that background color and that general shape. Now I get like a set of concentric circles. So if I select for that, I get a bunch of concentric circles. I may keep selecting for concentric circles, or I might go to this what looks like a fingerprint OREL. I may mutate that. I get a bunch of those. I like this one. I may keep going. I get that. I keep going. I can like explore sort of this fitness peak where I have like this OREL, and kind of it does. I don't know if it ever hits a fitness peak. It just kind of looks like it's exploring the space. I was kind of hoping to get it very refined. In a fitness landscape, you typically have this sort of space or the surface that has like sort of fitness values that follow this gradient. So this landscape of different fitness values, what you're doing is you're trying to, when you select for something, you're trying to climb this gradient to what they call an adaptive peak or a fitness peak. And the idea is that you're trying to increase the fitness of something. You're selecting variants that resemble that, and you're trying to get to this peak, this fitness peak. And so, the idea is if this space is flat, you shouldn't have a lot of fitness peaks. You'll just have a lot of variants being created. If you have a high peak, like if you have a single fitness peak, it might just be one type of image that you're just iterating on and trying to optimize for that. In a lot of fitness landscapes, you have multiple peaks where you need to go and explore them. You climb to the top of one peak and you have to reset the system to one of these valleys to get to another peak, and you can explore that. So if I go back to the Picbreeder, I might have explored this fitness peak for a while and then go to the blue colored ones and mutate those. And so you get concentric circles of blue. I already kind of explored that, so I'm going to go to this OREL. I'm going to explore that. Let me see if I can do that again. Okay, there we go. And I like this OREL, and I'm going to look for this thing, which is kind of a mix of the two things I found before. And you see the point is that you're kind of exploring that part of the space. You might move to a different part of the space, and then you try to optimize this design. Now, right now, I'm not able to do this because I'm not really trying, but I could get to some really optimized version of these ORELs. Or I guess in this case, not really optimized. It's just preference. What do I find the most beautiful? So this was actually produced by the Evolutionary Complexity Research Group at UCF. I don't know where this is based, but
is it UCF?
I think it is. I don't know.
Yeah, that was where Ken Stanley was originally. University of Central Florida.
Oh, okay, yeah, that's where that is.
I think that that was his home institution. Like again, like going back to 2007.
Yeah,
or like around there.
Yeah.
So
I don't think
he went to OpenAI.
I think they're defunct now, so it doesn't matter. But this is basically their demo. So, yeah. All right. Yeah. So that's all I had to say about that. Go ahead.
Well, I just wanted to add something that is not evolutionary, but was super interesting. Also, it was probably last week, but the videos dropped or just recently. But Isaac Newton Institute, and I dropped some links to this. Was covering a lot of interesting Turing pattern kind of stuff, and related related algorithmic work where that had a lot of biological inspiration, but a lot of biomimesis kind of stuff. That is certainly really cool.
Yeah.
And I let me just, I forget if I think I dropped one thing in bioevolution. Yeah. But was it maybe so I dropped something in I gotta add some more links to this because it was actually really cool, and I dropped something in network science that was related to like theory of hypergraph stuff, there was another. They were doing another seminar program that was actually more like Turing pattern kind of stuff relating to how you get stripes on an animal kind of stuff.
Oh, right. That was the one in bioevolution. That was
that was the one that it was
yeah.
kind of in bioevolution, but like if you go into their YouTube like header or description,
yeah,
like at the bottom of the paragraph, there's a link to the original, to the whole program, to the whole seminar.
Oh, okay.
And like you can get all the speakers, and like really cool, interesting stuff.
Yeah, yeah, the pattern formation using quantum stuff is interesting. Yeah, go ahead.
So it's interesting, right? Because it's like from that name, you might not know what you're getting yourself into.
Yeah,
but it actually is a lot about, again, it's about interesting mathematical structures for pattern formation, right? Because I think it was like what it actually meant by that was like orthogonal polynomials.
Yeah.
And what's interesting about that is that is actually very similar to a lot of this connectopic connectome harmonic analysis that was kind of Selena Adesoy was the first author on this stuff. Morton Kringleback, I think, was like the last author on this stuff. But it's a lot of very similar kind of stuff. But as applied to data analysis, right? As opposed to so just getting it. I mean, certainly breaking down resting state functional network into similar kinds of similar spherical harmonic decompositions, if you will.
Yeah. So
I just saw Jesse.
Yeah, Jesse had something here. I may have to go soon, but just recalling the Ranulph Granville stuff from before, I may have more fun cybernetics related things ahead about that ARIA collaborator and their projects. Yeah, I saw that, Jesse. You had a thing on what was the thing that you were mentioning?
Yeah, and this is not what you guys were immediately talking about, so I don't want to interrupt that if you want to say more.
Oh, no, go ahead. You can go ahead. I just have something to say after, but you go
ahead. I not a whole lot to say right now, but I just basically remembered that in the context of, we kind of, I rambled a lot earlier about cybernetics and teleology and complexity stuff. Suffice to say, there's another. I can't say too much about it right now, but someone asked about that, and I guess I wanted to say that came up when we were going through the references for the world modeling paper, right?
Yeah.
Is that where?
Yeah, that's right.
And was that a general reference, or do we explicitly reference that in the paper? Like I know part of the reference is like bibliography at large, but I don't remember if that's. I wanted to ask a little bit more about it in the context of that paper, but we don't have to discuss that now.
Yeah.
I just knew that.
Yeah, so I mean, like the Granville paper, we talked about black boxes and white boxes. Like the idea being that black boxes are unknown processes, white boxes are where you know what's inside the box, the process. And then the idea that Granville had was that if you have a black box and you figure out what's inside of it, and it turns into a gray box or a white box, then it's transparent. You know what the process is. So instead of having like a stochastic process, you have something that has a mechanism inside. But his point was that even if you can do that, you still have new black boxes that pop up within that. So you keep going. It's kind of a reductionist approach to breaking down a black box. you do that and you still have black boxes, and you continually, it's like black boxes all the way down, basically. So that was the thing. And then it was cited in the paper as kind of like, the things about cybernetics where we have these boxes and arrows, and, the idea that there's this regulation, and, regulation, how much knowledge we have to have about what's inside the black box to really understand if something's well regulated or not. I think that's kind of the point of linking that to the paper. And then, I don't know if you had like someone who's interested in that, or something about Granville, or what it was.
I'll probably say more later, just because I don't want to be too unstructured in talking about it right now. But no, that's good. I'm going to go look at the paper again and kind of relate it back to what's going on. And it's kind of funny. It feels like this, unplanned in the greatness cannot be planned sense, unplanned big foray into like cybernetic related stuff over the last month or so. And it's kind of funny because it's not what I was thinking of, but then a lot of fun stuff there. So yeah, I'll let it be for that. And I have to go soon, but thank you for everything today. Questions. Yeah,
no problem. So then I had one more comment on what Morgan was talking about. The quantum stuff for pattern or pattern formation reminds me of, I've done this work and I never published it. I just kind of like played with my food, as it were. Working on this thing with kind of like interference patterns and pattern formation, or like in morphogenesis specifically, and other types of like, overlapping sort of motifs that kind of interfere. It's something I have to write up, and I've been working on it for many years, and I don't exactly know how to write it up, but this is this idea that you could have like chemical gradients that interact, or, something else. There's some examples of this in nature where you can have these overlapping patterns that form higher order patterns and things like that.
I think you'd like this seminar series.
Yeah. I'll take a look at it.
Yeah, awesome.
So, in a lot of the embodied cognition, we have had discussions about like synergies and complexity theory, and a lot of the examples that you have kind of relate to biomechanics, but also do embodiment. And we've talked about pre-nervous system filtering of information. And so we're going to talk about now, it's kind of a mix of all those things. We're going to talk about this area called neuromechanics. And we're going to talk about some biomechanical filtering, some things about synergies, and some things about motor control. And so it'll come together, hopefully. So this is a couple authors. Neville Hogan is a big name in motor control. And this paper is in 2024. It's a preprint in bioRxiv. This is on human motor coordination, the synergy expansion hypothesis. So this is a paper on motor coordination and motor control, but it's also bringing this idea of synergies together with that, and synergy expansion specifically. So this abstract talks about Bernstein, and we've talked about Bernstein before. He's an early motor control person. So the search for an answer to Bernstein's degrees of freedom problem, and the degrees of freedom problem is like, when you're trying to control your coordinate your limb movements towards a target, you have a number of degrees of freedom. And the idea is, are those degrees of freedom coupled, or are they independent? If they're independent, then it's harder to control than if they're coupled in some way. So people have searched for an answer to this. And of course, we talked about synergies as being the coordination of these degrees of freedom with muscle groups, with limb joint coordination, and these other sorts of things. So this search has propelled a large portion of research studies in human motor control over the past 6 decades. Different theories have been developed to explain how humans might use their incredibly complex neuromuscular skeletal system with astonishing ease. So, we do this sort of easy kind of, we make movements with these, but it's a really hard problem for the nervous system to solve. You have to have this sort of multi-level coordination of muscle groups and joints and things like that. So, we have to kind of think about how this might work. Among these theories, motor synergies appeared as one possible explanation. So motor synergies are where, you have muscle groups that are coordinated in their activities, or you have limbs that are coordinated, and it constrains the kind of movement space that you can make. So, if I coordinate myself to move and grab a cup on the table and move it to my mouth, that's a set of muscles that in my arms and in my torso that need to be coordinated. The brain needs to coordinate all that, and the control problem is harder if they're not coordinated into one unit. But if they're coordinated into one unit, it's a lot easier. So motor synergies was one possible explanation. In this work, the authors investigate the nature and role of synergies and propose a new theoretical framework, namely the expansion hypothesis, to answer Bernstein's problem. The expansion hypothesis is articulated in 3 propositions. So the first is mechanical, the second is developmental, and the third is behavioral. So you have kind of the whole sweep of the field of motor control. You have sort of this mechanical aspect, this neuromechanics, this biomechanics aspect, and then you have the developmental aspect, which is Piagetian, where you have this like motor control is an important aspect of development. So if we coordinate ourselves to walk or coordinate our movements, we're not really born making these very refined movements. Babies' movements are very uncoordinated. And so they need to be able to coordinate their movements. And this is kind of the other concern. And then behavioral, of course, because that's a behavioral problem. Each proposition addresses a different question on the nature of synergies. So the first is how many synergies a human can have. So, how many synergies can you have? Can you have one synergy, or can you have infinite synergies that kind of arise as you need them? So like if I reach out and grab a cup and move it to my mouth, that's one synergy. If I'm like running down a soccer field and I do a cartwheel and I kick a ball into a goal, that's another set of synergies. If I'm trying to fly a plane, that's another set of synergies. If I'm playing the violin, that's another set of synergies. So how many can you have, and is there some sort of computational cost to that, I guess? 2, how can we learn and develop synergies? So how do we develop them? How do we learn them? Are they learned? If you're playing the violin, you're learning a set of, you're coordinating certain muscles. Those are, you're training those muscles, you're training your nervous system to respond to that synergy. So you're not born knowing how to play the violin well. You learn that synergy and you develop it to become an expert at playing the violin. 3, how do we use synergies? So, how do we coordinate them and implement them? Do we use them for specific things, and why? Okay. So these are the things that, you can ask about synergies. An example numeric simulation is presented and analyzed to clarify the hypothesis propositions. The expansion hypothesis is contextualized with respect to the existing literature on motor synergies, both in healthy and impaired individuals. So this is not only useful for looking at like how we do, how sensorimotor coordination works, but also if if you have impaired individuals, if you have people with, a lack of muscular control, for example, or they're paralyzed, they have they don't have full function or range of motion in their arm muscles. Those sorts of things, those are important. They're going to have different types of synergies. Sometimes they compensate for the loss of muscular control, or they compensate for, if they have compromised muscle activity, they can, they have different synergies, maybe for doing the same thing. So it's an interesting way to look at this, as well as other prominent theories in human motor control and development. The expansion hypothesis provides a novel framework to better comprehend and explain the nature, use, and evolution of human motor skills. So this is where they kind of talk about the expansion hypothesis, where they define motor synergies in the introduction as coordinated activities of multiple features, such as joints and muscles, that simplify movement control. So you're trying to aim towards this fluid motion and coordinating all of the substrate to do that. And this is also useful for robotic control, because in robotic control, we're trying to coordinate a potentially large number of degrees of freedom. If we can constrain those degrees of freedom so that, some, joints move with other joints in coordination, then that can solve the computational load in terms of producing smooth robotic movements. So, let's see, they kind of talk about synergies. They talk about defining the different components. So they define a motor task as any task requiring the temporal coordination of multiple features, which they define as muscles and joints. So, in synergy, you're coordinating temporally muscles and joints. And so the temporal aspect is important because you have to have the timing right. So for example, a motor task could be a reach and grasp movement, or the movement performed when swinging a golf club, throwing a football, or playing a musical instrument. Such a motor task can be decomposed as a sequence of temporally grouped motor chunks. So this is interesting because, we've talked about sequence learning in the context of artificial neural networks. So sequence learning in, like large language models, that can be a bottleneck to learning context. We talked about that. We also talked about sequence. There's a hypothesis where people have reimagined spatial cognition as a sequence learning problem. And so a sequence learning problem just is where you have these like tokens or these primitives that are assembled in a sequence that the model has to understand and has to be able to compare with other sequences. So this kind of lends itself to the sort of these different models, these artificial models, but also some things that we do. We oftentimes perceive things in sequences and in time. There are also these motor chunks which actually build on what we know about short-term memory, what we know about like taking information in from the world, like episodic memory or procedural memory, and associating them in a chunk. So like, a motor chunk would be like where if you had a lot of things that were related to one another that could be put into a category, you would do that. In motor control, it's a bit different because we're talking about procedural learning, but basically it's chunking procedural learning. So this is also something that happens in time. So, there are these concepts that related to cognitive processing. Lashley is a good resource for thinking about some of these early ideas. Diedrichsen and Kornisheva have done some more recent work on this. So this is where we have, what they're trying to do is build a model of motor chunks being sort of the decomposition of a motor task, which can be represented by a continuous temporal evolution. So in piano playing, or if you're tapping your fingers on a table, a motor chunk can represent a subsequence of the finger movements that have their own distinct temporal patterns. So in piano playing, you're reaching out with your fingers to hit different keys. A motor chunk might be a movement towards a certain key. And then the idea is you can break this down into pieces and understand the coordination that way. Each motor chunk can be in turn decomposed into a series of elementary actions representing the fundamental atomic elements composing motion. So these elementary actions are made of two distinct parts: the synergy composition, which is vector WI, that contains the information of the selection of each feature of the given motor action, and then the temporal evolution, which is UI t minus ti, which represents the time trajectory of the synergy composition vector. So they're taking the motor action, they're breaking it down into these chunks, and then they're reconstructing it as this, temporal evolution. So you have, information in each feature, and then this temporal evolution. And then so, we can build a model that's formalized this way. We also have this diagram that shows sort of the hierarchical organization of motor planning. So we have a motor task, which is sequence ST. We have these temporal groupings or these chunks. We decompose the sequence. We decompose each chunk into elementary actions. For each elementary action, we have a synergy composition, which is these matrices W, and they describe this set of things that are involved in the elementary action. These set of elementary actions define a chunk. The chunks define a sequence. And then so you can look at these temporal evolutions. So you can look at the evolution of synergy compositions, the evolution of temporal groupings, and then motor tasks in this way where you have these distributions over time that kind of overlap. And that's kind of the idea here, where you can look at the temporal evolution trajectory as a series of synergy compositions that overlap and produce these outputs. So if you're playing a piano, you have finger movements. The finger movements have different components to them, and you can look at those as they kind of are coordinated together in time. So this is an interesting paper that kind of goes over this sort of idea of synergies and how they think about, development and, active behavior and things like that. The second paper is on biomechanical filtering. So we talked about, I think it's Adam Safran who proposed this idea of pre-filtering things in embodiment. And so it means that you have information maybe that's coming into the peripheral nervous system through joint receptors or through, proprioception, and that's filtering information kind of at the level of the spinal cord or in the peripheral nervous system before it gets to the brain. So this is a very clear role for embodiment. Now, in this case, what they're talking about is biomechanical filtering, supporting tactile encoding efficiency in the human hand. So this is, this is kind of a hardcore biomechanics paper. This is a bioRxiv preprint from this year. And so this kind of goes into some, biomechanical, explicit aspects of this sort of idea of embodied filtering or whatever we want to call it. So the abstract reads, touching an object elicits skin oscillations that are biomechanically transmitted throughout the hand, driving responses in thousands of tactile receptors, including numerous exquisitely sensitive Pacinian corpuscles. Accepted definitions of Pacinian corpuscles functionally characterize the response properties as highly stereotyped based on experimental data gathered when stimuli are applied near the receptor. So if I have my hand and I touch it with a feather, I brush a feather across the hand surface. That touching the hand surface like that elicits skin oscillations along the surface of the skin in the different sensor receptors on the surface of the skin. This is biomechanically transmitted across the skin, so it provides some spatial information, but more importantly, it provides a sort of intensity information. And so you can tell sometimes when you've been touched by a feather versus touched by a pen because of the pressure, because of the sort of the spatial information, and so forth. So this is all information that comes from these receptors called Pacinian corpuscles, as well as other types of surface receptors on the skin. So this just kind of talks about, the response properties of these receptors, and then they get into that. So there's this phenomenon called natural touch. So, however, during natural touch, so you can actually do this in a very sort of mechanical way they do in the lab. Natural touch is where you have this sort of, where it's maybe like, just naturally touching something as opposed to like stimulating the receptors. During natural touch, spiking activity in the majority of Pacinian corpuscles is evoked by transmitted skin oscillations that are modified by biomechanical filtering. This filtering mechanism, stemming from dispersive wave dynamics in the skin, bears some similarity to the preneuronal filtering of auditory signals by the basilar membrane, a mechanical process that is instrumental to perception. So this is where, they're comparing proprioception with auditory filtering or auditory processing in the ear. So you have this preneuronal filtering of auditory signals by this basilar membrane. It's basically, a component of the inner ear, I believe, where it's basically filtering the frequencies. And it's, this is before it's even an input to the brain, to the nervous system. And so this is, again, something that we see in the surface of the skin. When you engage in natural touch, there are these modifications to the skin and the way that this signal is processed before it even gets to the nervous system. So thus we sought to clarify how skin biomechanics might influence tactile information encoding in the periphery. We used vibrometer imaging and computational neural experiments to examine the influence of biomechanical filtering on neural activity in whole hand Puccini and corpuscle populations. We observed complex location and frequency dependent patterns of filtering that were shaped by tissue mechanics and hand morphology. So it's the sort of the nature of the skin, the mechanics of the skin, and hand morphology. So wherever you put it on the hand, that's morphology dependent, depending on the nature of the tissue and where you place the stimulus on the hand. That's also a factor that is variable. The source of biomechanical modulation diversified Puccini and corpuscle population spiking activity and enhanced tactile information encoding efficiency. So depending on where the stimulus happens on the hand, it's dependent on these mechanics and morphology aspects, but also this affects the neural activity at the receptors and the information encoding at the receptors. So this tactile information encoding is more or less efficient depending on these other factors. These findings indicate that biomechanics furnishes a preneuronal mechanism that facilitates efficient tactile encoding and processing. So this is a nice paper on, kind of goes over this model of biomechanical filtering. And so, they kind of have some diagrams here where they have different contact locations, which translate into different stimulus frequencies. They show kind of the spatial resolution of the hand, and, depending on where the stimulation occurs, there are different amplitudes of the signal. All right, so then the third paper here is discovering individual specific gait signatures from data-driven models of neuromechanical dynamics. And this is a bioRxiv preprint from 2023. And this will hopefully tie up the other two papers, or tie together what they've talked about. And so locomotion results from the interactions of highly nonlinear neural and biomechanical dynamics. Accordingly, understanding gait dynamics across behavioral conditions in individuals based on detailed modeling of the underlying neuromechanical system has proven difficult. So it's kind of like, we've done these detailed models. We're trying to get a sense of gait dynamics, which is where you're walking and you're trying to figure out the dynamics of footfall and the dynamics of stride and things like that. Here we develop a data-driven and generative modeling approach that recapitulates the dynamical features of gait behaviors to enable more holistic and interpretable characterizations and comparisons of gait dynamics. So they're using this sort of generative modeling approach. They want to look at gait behaviors as these dynamical processes, but having different features that they can extract out and understand what they mean. So they want to basically characterize comparisons of gait dynamics across individuals, across people with, pathologies versus normal and so forth. Specifically, gait dynamics of multiple individuals are protected by a dynamical model that defines a common low-dimensional latent space. So this is, again, where we're doing the same kind of thing we did with CPPNs. We're generating this low-dimensional, or in that case, it's a high-dimensional latent space, perhaps. But in this case, you're generating a low-dimensional latent space. And, in the first paper, they kind of didn't do this, but they did talk about muscle synergies. If you wanted to find, the number of possible muscle synergies, you generate some sort of latent space where you could sample from that latent space and find different muscle synergies that might be sort of used in different contexts. So maybe that's what we have from the first paper, and then of course you're doing something like this in this paper. This is to compare group and individual differences. So, group and individual differences all exist in this latent space. And, essentially you can draw like kind of solutions from that and compare it with what people are doing. We find that highly individualized dynamics, or gait signatures, for healthy older adults and stroke survivors during treadmill walking. So they put them on the treadmill, they have them walk. They're able to look at different populations. In this case, they have healthy older individuals and stroke survivors. And they want to see, what kind of individual dynamics they have. Oftentimes, again, older adults and stroke survivors are compensating when they have these synergies for moving. They're often compensating for like some sort of, disability or something where their muscles aren't working maybe the same way they worked when they were healthier adults or in normal so-called normal populations. So they look at treadmill walking. They see that treadmill walking is conserved across gait speed. Gait signatures further reveal individual differences in gait dynamics, even in individuals with similar functional deficits. Moreover, components of gait signatures can be biomechanically interpreted and manipulated to reveal their relationships to observe spatiotemporal joint coordination patterns. And this is basically our synergies, where we have these joint coordination patterns in space and time. So we have temporal coordination, we have these motor chunks that are coordinated. We also have things that are spatially coordinated. So if you have things in your upper leg, things in your lower leg, things in your hip that are all coordinated together. Lastly, the gait dynamics model can predict the time evolution of joint coordination based on an initial static posture. So you start by standing still, and then, you get the sense of what muscle groups are, weak or strong, where you're starting from, and then it can predict kind of the sort of synergies from that and how those synergies evolve over time. Again, we're doing this from a latent space. We're not doing this we're using data to generate this latent space, and then we can generate things from the latent space to predict things from a static posture, so you know kind of where your starting point is, and you can predict out from there. Our gait signatures framework thus provides a generalizable, holistic method for characterizing and predicting cyclic, dynamical motor behavior that may generalize across species, pathologies, and gait perturbations. So that's a set of papers on neuromechanics and synergies and complexity at the level of motor control, and then looking at how they're using generative techniques to sort of generate these sort of synergies and predict things from them.
Yeah. Do you mind bringing up the first paper real quick?
Yeah, let's see.
Like synergies.
Synergy expansion hypothesis.
Yeah. So if you can blow it up for my old eyes.
Yes.
Yeah. And scroll down a bit. Just wanted to. I think I saw something in terms of what they were doing to. Oh yeah, sorry. Stop there. Go up. Yeah, up a bit.
In the equation?
No, yeah, keep going. Yeah, above that equation though.
Right up here.
The above the synergy. Yeah. So just wanted to get right there. Okay, yeah. So the current mathematical methods to extract synergies are based on matrix factorization techniques. Yeah. Okay. Yeah, I mean, sure. Like I guess is the theme here. Is finding that lower dimensional space.
Right.
And my basic super simple search trying to find that paper I found this 2010 paper that they were talking about, kind of like, again, like finding the low dimensional manifold,
Right.
and yeah, just you know, this is what you get when you have these kind of rigid bodies connected, where it's like there's lots of moving parts, but because of their connectivity, they're actually much fewer degrees of freedom than you think, and yeah, it's really interesting. I mean, how that relates to EEG analysis as well.
Really? Oh, like block models? Or?
Again, like that. It's much lower dimensional than you think.
Right.
Like it looks. And how, again, these matrix factorizations are so important because they really uncover that, and again, like, been doing some stuff recently just in terms of how best to find that complex, or that low dimensional, like what's the correct number of dimensions.
Yeah.
Right, because if you can and certainly, like, variance explained sometimes doesn't do it justice. Like, you need a little bit more subtlety in terms of finding that correct, much lower dimensional space.
Yeah.
And then the interesting things that happen when you're starting with, like, say 64, you're getting something where it's like 30 explains all the variance, but you can actually find a representation in 8 dimensions, and like what happens with that much more compact one. It's really interesting. The gait, so the piano playing is really interesting, because of, it's also the links, or at least the discussion William James had about it, in terms of, like, both motor chunking as well as just speed of execution, and source, the neural source of, like the conduction times and things like that.
Right.
But a lot of groups use gait analysis for dementia prediction. Like it's really interesting, all the other pathologies that create a detectable gait change, right? I mean, there's they were including stroke, but you can certainly see this with like the obvious ones being, like, MS and Parkinson's, where there's like literally these motor aspects, but I thought dementia is really interesting because you don't think about it as being that kind of issue, but it really does have all these kind of system-wide effects that come out, and potentially it relates to this kind of breakdown of chunking and these general mechanisms that the brain is using,
Yeah.
like you're seeing here.
Yeah.
Anyway, super interesting. I look forward to the actual links.
Yeah. All right. Yeah, I think that's it for this week. Thank you for attending, and we'll follow up on the active inference stuff later.
Yeah, for sure.
All right. Thanks. Bye.
Take care.
Take care.
Bye.
Bye.